Hello everyone.
Hello everyone. I'm Wang Boxuan.
I'm Yao Zhiyu. Our topic is application of linear transformation and vector spaces in science and engineering.
Okay. Here is our content. I will introduce the first two parts.
I will introduce the last two parts. Now let's start our presentation.
Okay, the part 1, theoretical basis. In this part, I will briefly introduce the definition of the vector space and the linear transformation. The first one is the vector space. A vector space is an empty set V of objects called vectors, on which are defined two operations, called addition and multiplication by scalars, subject to the rule that all of the vectors operate by the axioms on the right, such as the sum of two vectors originally in V belong to V, the existence of additive inverse, compatibility of scalar multiplication with field multiplication, and so on. Like the picture shown below is a vector space with 3 dimensions. We write it as R power 3. Okay, next is the linear transformation. A linear transformation, also called a linear map, is a function between two vector spaces that preserves the operations of vector addition and scalar multiplication. In other words, it satisfies the properties below for all U and V belong to set V, and all scalars A belong to set F. The first one is additivity. It's additivity, the preservation of vector addition. The second property is homogeneity. That is the preservation of scalar multiplication. If both addition hold, the T is called a linear transformation. Okay, now is the part 2, the applications of the vector space and linear transformation in science. In this part, I will mainly discuss their applications in areas of physics, climate science, and chemistry. Okay, first of all is the applications in physics. First, in classical mechanics, the motion of objects in space is often described using vector space. The position of an object in 3D space is represented by a vector in R power 3. Similarly, velocity and acceleration are also vectors. These vectors are elements of vector spaces, and linear transformations can be used to change the reference frame of these vectors, for example, in rotating or translating coordinate systems. Next, in electromagnetism, the electric field and magnetic field at a point in space are represented as vectors in 3D space. These fields can be added together, vector addition, and scaled scalar multiplication to analyze complex interactions. What's more, linear transformations are used to describe the propagation of electromagnetic waves, such as light, through different media. The direction and the polarization of waves can be understood using vector spaces as well. What's more, quantum mechanics is deeply rooted in the theory of vector spaces and linear transformations, particularly when it comes to the state of a system and operators that act on these states. This state, the state of a quantum system, is represented by a vector in a complex vector space called a Hilbert space. Okay. Next is the applications in climate science. The first application is climate data analysis and dimensionality reduction. Principal component analysis, briefly called PCA, is a statistical method that is widely used in climate science for dimensionality reduction and pattern recognition. PCA involves linear transformations of data vectors to identify the most significant patterns or components in large data size, which is particularly useful for analyzing complex climate data. Another application is climate prediction and simulation. By analyzing the data and deriving a linear regression mode of the climate, we can more accurately predict the climate. By applying linear transformation and vector space, we can transform the model into a more accurate climate prediction model. Kalman filtering can also be combined with vector space to present a specific result, thus enabling climate prediction and simulation. The last one is applications in chemistry. In quantum chemistry, diagonalizing or performing singular well decomposition of the matrices. Important information such as molecular orbital energies and electron density can be obtained. In density functional theory, briefly called GFT, is a method for calculating molecular electronic structures. GFT typically involves solving a series of linear equations to obtain electronic distribution and energy of a molecular system. What's more, the pathways and mechanisms of chemical reactions often involve multiple reaction steps and transition states. Linear algebra is essential in analyzing these problems. In chemical sensors and signal processing, the signals from chemical sensors often need to be processed using linear algebra to extract meaningful information.
Now I'm gonna introduce the applications in engineering. I'm gonna explain applications in robotics, signal processing, and computer vision. In robotics, a robot's motion can be described using vectors. Each joint position, like the picture given, velocity and acceleration forms a state vector. To compute the position of the end effector, we apply a series of linear transformations using rotation and translation metrics. The Jacobian matrix linearly maps joint velocities to end effector velocities, a critical part of real-time motion control and inverse kinematics. We can also see how these tiny changes affect the end effector. Signal processing. A signal, such as sound or ECG data, can be viewed as a vector in a high-dimensional space. The time and frequency domains are fundamental properties of a signal, which allows it to be analyzed in a variety of ways. Using linear transformations like the Fourier transform or discrete cosine transform, we can project the signal into a new basis, the frequency basis. This helps us extract important features, reduce noise, or even compress data, as in MP3 audio or JPEG images. Computer vision. In computer vision, an image is represented as a matrix of pixel values, which can be flattened into a vector. To scale, rotate, or doing other changes to images, we apply linear transformations using transformation matrices. Furthermore, for tasks like face recognition, we use a new technology, which is called PCA. PCA is Principal Component Analysis. It's to reduce image dimensions by projecting onto the most informative directions. You see how these high dimension data are compressed into low dimensions from the picture. Summary. In summary, across all these domains, linear algebra serves as the unifying language. Vectors represent data, and metrics represent transformations. Whether we are processing audio, images, or robot movement, linear transformations and vector spaces give us control, insight, and efficiency. With the rise of artificial intelligence, linear algebra becomes even more critical. Modern deep learning frameworks rely heavily on vectorized operations, matrix multiplications, and eigenvalue analysis. Linear algebra is no longer just a tool, it's becoming the language of intelligent systems. Mastering it will open doors to science, robotics, AI, and beyond.
So that's all of our presentation.
Thank you.